CSI member. And let me just get this little window off of this screen. I've been a CSI member for more than 30 years now. And of course, I appreciate the role that CSI plays within the profession of architecture and related fields, helping architects, contractors, and product manufacturers to make better buildings. But this afternoon, my presentation will discuss tendencies that work against making good buildings, based in part on a book that I recently published called Building Bad: How Architectural Utility is Constrained by Politics and Damaged by Expression. And when I say bad buildings, I'm not talking about how they look or referring to the type of critique popularized by people like Prince Charles and Donald Trump, where particular aesthetic systems or styles have come under attack. Clearly, we all have our own subjective appraisals that we bring to the built environment. And whether these subjective appraisals are concealed within obscure philosophical jargon or advanced by architectural critics based on their own refined connoisseurship, or regulated by federal statutes based on any number of political or economic considerations, I don't believe that indulging in such subjectivity can produce a useful theory of architecture. So I'll try my best to avoid subjective judgments in this presentation. When I talk about building bad, I start with utility, that is, the objective functional basis for which buildings are built in the first place. And I argue that the utility of a work of architecture can be damaged not only by politics and economics, but also by the dysfunctional competition that drives fashionable expression. So let's start with the politics and economics of bad buildings, and then talk a bit about dysfunctional forms of expression, topics that correspond to the two parts of my book. I began thinking about this talk a couple of months ago in early January, shortly after a fire in a Bronx apartment house killed at least 19 residents. And this particular fire started with a defective space heater, but there were other bad practices that contributed to this building disaster. Certainly, the lack of maintenance that allowed self-closing fire doors to remain open so that smoke could spread to upper floors, or the lack of adequate heat that forced tenants to plug in space heaters, point to pervasive economic incentives in our society to cut costs in order to maximize profit. But there are also specific political decisions that permitted a dysfunctional architectural design, decisions that also contributed to this disaster in what was considered at the time a notable building, reviewed in the New York Times at the time by Paul Goldberger, who pronounced it an example of good architecture. Now, I would like to take issue with the idea that good architecture is somehow independent of the utilitarian or functional defects in a building's design. As I argue in my book, the legal infrastructure upon which buildings are built is concerned primarily with encouraging economic growth. Safety measures are therefore implemented only to the extent that they are consistent with a kind of cost-benefit mentality, even when the prevailing state of fire science and engineering points to safer modes of construction. In other words, there is a difference between the guidance and requirements found in legal documents, such as building codes, documents that define in part a prevailing standard of care within a particular time and place, and the prevailing state of engineering and science, which point to optimal strategies for strength, durability, and safety. So following building codes is of course necessary and most often sufficient to protect professionals from legal liability, but it shouldn't be confused with making buildings as safe and resilient as possible. A glimpse at the prevailing state of fire science when the Bronx building was designed and built can be found by examining the 1969 edition of the Fire Protection Handbook published by the National Fire Protection Association, which came out several years before the construction of the Bronx apartment building. So what were the fire safety principles advocated in the handbook that were excluded from the building code and that were not implemented in the building? First, as you can see in this sketch of the floor plan, which I have annotated, the building had dead-end corridors, even though, as the handbook states, quote, a dead end forms a pocket in which occupants may be trapped, Since there is only one access to an exit from a dead end, a fire in a dead end between an exit and an occupant prevents the occupant from reaching the exit. Ideally, dead ends should be prohibited, end quote. Second, the building had no automatic sprinklers, which were legal back in the early 1970s. These sprinklers would most likely have would have put out the fire before it became deadly. The handbook said in 1969, quote, automatic sprinklers where a complete standard system is installed do have a major influence on life safety. In addition to providing an automatic alarm of fire, they quickly discharge water on the fire before smoke has spread dangerously. Third, the building did not place its two required fire stairs as remote from each other as possible, but grouped them together in a single shaft, even though the handbook advises that, quote, at least one alternate exit should be provided remote from the first, end quote. Fourth, perhaps most importantly in this context, the building's fire stairs were not designed to keep smoke out. All of the 17 initial deaths in the Bronx fire were due to smoke inhalation, many occurring in the fire stairs themselves. The handbook, reflecting the prevailing state of knowledge, states that the safest form of stair enclosure should not be placed in the middle of the building, but rather configured as a smoke-proof tower, where, quote, access to the stair tower is only by balconies open to the outside air, so that smoke and fire will not readily spread into the tower, even though the doors are accidentally left opened, end quote. This is just one example of many that could have been taken from news reports, all of which have the same underlying message. It is not a lack of knowledge, but rather the competitive drive for profitability, cutting corners to save money, that leads inexorably to these disasters. Whether we're talking about the Bronx fire in January 2022, the Grenfell fire in London in 2017, the collapse of the Champlain Towers condo in the suburbs of Miami in 2021, or even the sinking and tilting of the upscale Millennium Tower in San Francisco, beginning in 2009 and continuing into 2022, even as it is being repaired at a cost of over $100 million. In part one of my book, I look not only at the politics of fire safety and structure, but also at the politics of accessibility, security, light and air, and sustainability, with the first chapter providing an overview of health, safety, and welfare in capitalist society. I argue that politics and economics set upper and lower bounds on architectural utility wherever health, safety, and welfare issues are at stake. What is perhaps more interesting and less self-evident is that the utility or functionality of buildings is also damaged by contemporary forms of architectural expression. I examine this phenomenon in part 2 of the book, and this is a primary topic of my talk today. Perhaps the easiest way to frame my argument is by first presenting some examples outside of architecture where forms of expression or fashion, driven in part by the desire to reinforce social or class distinctions, can overwhelm considerations of function. Here's an excerpt from chapter 15 of the book on fashionable building with an avian example. The utility of fashion for competition has two aspects. First, architectural fashion provides visual clues that indicate one's membership within a group, class, or subculture. And second, within a particular group or class or subculture, fashion acts as a means of competition. And since the first aspect is a prerequisite to the second, it is necessary to be in a group acknowledged as being in fashion before one can compete within that group. The utility of fashion for competition is absolute and unequivocal. The same phenomenon shows up in various non-human species, for example, in the sexual ornaments and displays of certain birds. This can be taken as evidence in support of the argument, but also as evidence of its dysfunctionality. According to the evolutionary ornithologist Richard Prum, there is no necessary evolutionary benefit in the use of fashion within avian culture, other than enabling sexual selection, that is, competition, on the basis of arbitrary aesthetic criteria. And these criteria may well be maladaptive, quote, resulting in a worse fit between the organism and its environment, end quote. This same insight was brilliantly captured by Theodore Geisel, otherwise known as Dr. Seuss, in his 1958 story about a girl bird named Gertrude McFuzz, who, competing with another female bird, decides to grow dysfunctional quantities of tail feathers that ultimately prevent her from flying. The Austrian-born art historian E.H. Gombrich argues that such unintended and disastrous outcomes of competition, characterized by, quote, threat summed up in the word escalation, end quote, are often found in human societies. Within the human realm, one of the more extreme examples of damage associated with fashionable expression is foot binding, a practice that existed in China for 1,000 years. Amanda Foreman, writing in Smithsonian Magazine, describes the process as follows, quote, first, her feet were plunged into hot water and her toenails clipped short. Then the feet were massaged and oiled before all the toes, except the big ones, were broken and bound flat against the sole, making a triangle shape. Next, her arch was strained at the foot and was bent double. Finally, the feet were bound in place using a silk strip measuring 10 feet long and 2 inches wide. These wrappings were briefly removed every 2 days to prevent blood and pus from infecting the foot, end quote. Architectural expression similarly may contort a building's form in ways that are damaging to utilitarian function. And this bad behavior starts with a type of abstraction that I discuss in chapter 11 of my book on modernist abstraction and dysfunction. It begins, architecture cannot be understood without reference to the notion of abstraction. We discuss buildings in terms of form, space, geometry, context, color, meaning, or anything else only to the extent that we abstract from the qualities that are actually present in the material. Tabulating or adding up the objective qualities of building elements does not get you any closer to an understanding of architecture. So abstraction is a fundamental necessity in both critiquing and producing architecture. Understanding architecture as having a conceptual basis is the same as understanding architecture as an abstraction. A concept describes what the architecture is by abstracting from what it is not. As an example, if the concept of the Pantheon in Rome is of a sphere within a cube, such a description simultaneously abstracts from all that is not relevant to the concept, the particular qualities of each brick, stone, and concrete element from which it is constructed, the ornamentation of the exterior and interior surfaces, and so on. If a designer is unable to abstract from these useful and specific material qualities, a design concept will never emerge. That architecture has a conceptual basis does not mean that prosaic material properties and material relationships are not important. It only means that to the extent that architecture is understood conceptually, such information is placed in a different file folder. If it is accepted that abstraction is a requirement for the appreciation, understanding, and creation of architecture, the question remains as to how all the elements abstracted from those things placed in our metaphorical file folder become part of the building, as they must. For as the philosopher Hegel wrote almost 200 years ago, one cannot build an abstraction. Up until the end of the 19th and the start of the 20th century, the type of abstraction underlying architectural design was generally built upon, paradoxically, an acceptance of conventional building elements, building materials, and building construction techniques. Windows remained windows, doors remained doors, walls remained walls, roofs remained roofs. In general, structural forces were resolved in conventional ways. Construction proceeded along conventional lines, and environmental constraints on site planning, building orientation, and so forth were respected. The conceptual basis of such architecture neither challenged nor threatened these prosaic elements and conventions, but was rather developed with these elements in mind. Window openings may have been elaborated or framed with ionic columns and decorated with various ornamental forms, and the geometric organization of the facade may have abstracted from material or constructional logic of brick, stone, or plaster surfaces from which its expression emerged. But the window was still understood as a window, and the wall was still understood as a wall. That architecture took as its point of departure, walls, columns, windows, and roofs, was rarely questioned. Alberti and other 15th to 19th century architects and writers maintained a conventional and uncontroversial attitude towards such building elements, even as they explored issues of architectural design and abstraction. The origins of a more radically abstract way of understanding architecture were already present, but were not recognized as serious alternate strategies for designing buildings. Rather, examples of conceptually pure forms devoid of references to conventional building elements appear almost exclusively in works of monumental scale, expressing the most unfathomable and sublime concept of all, death. The Great Pyramid of Giza, completed 2560 BCE, and the cenotaph for Newton, designed but never built by Etienne Louis Boullée in the late 18th century, can be cited as precursors to the radically abstract forms characteristic of later works of architecture. However, such precedents were not considered at the time to be legitimate role models for non-funerary building types. Architectural abstraction as mere elaboration or ordering of conventional building elements began to be challenged in the late 19th century, and especially in the early 20th century. And while the canonical houses of 20th century modernism were hardly representative of domestic building then or now, they were extraordinarily influential in creating a kind of beachhead from which radical attitudes towards abstraction could take root and ultimately become major factors in both the pedagogy and practice of architecture. This new form of abstraction differed markedly from traditional forms of abstraction. Le Corbusier's 5 points of architecture describe the potential of new technologies, in particular, the replacement of load-bearing walls by structural frameworks, to overcome what were considered insufferable constraints of traditional construction. In many of his buildings, windows are abstracted as rectangular openings or voids. Other conventional building elements are defamiliarized or eliminated entirely. Stucco replaces clapboards as it betrays no material origin and can be more easily understood as abstract surface. Roof shingles, along with sloped roofs of any sort, are simply eliminated as they contain such strong references to the traditional tectonic geometry of attics and gables. Brick chimneys are replaced with painted metal cylindrical pipes, and all traditional ornamental or decorative embellishments are banished. The point here is not to criticize any particular aesthetic outcome or to propose a return to any particular stylistic tendency. The key change from the standpoint of building failure and building function is that for the first time, architectural abstraction was made independent of building construction and building conventions. Many advances in building technology can be cited to explain the motivation as well as the potential for changes in architectural form and construction associated with modernism. Perhaps the most obvious were major improvements in the production of ferrous metals used to create structural frameworks, leading to the widespread use of standard I-beams and later wide flange sections made from rolled steel. And at about the same time, near the turn of the 19th into the 20th century, reinforced concrete also became, for the first time, a viable structural material. It is hardly accidental that the formal inventions of modern architecture drew upon the structural potential of these new materials. If structure were abstract grid or abstract plane in the case of load-bearing walls, and if glass were abstract void, other constructional elements or materials required to complete the desired abstract compositions of modern design were harder to find. The neutral solid surface had to consist of something, but nothing new is available except perhaps the mottled gray surface of reinforced concrete. More often, such surfaces were created, as they had been for thousands of years, by applying a layer of stucco to an underlying substrate of brick or later concrete block, even in Corbusier's Ville-Savoye. The important point is this. In spite of an abstract conception of buildings which eschewed conventional building elements and conventional material expression, modern buildings still needed to be actually and physically constructed. And moreover, modern architects had hardly given up or gone beyond a traditional understanding of building construction as consisting fundamentally of physical things whose value was measured as it had always been measured, by their strength, by their resistance to movement, and by their durability. Expressing such characteristics of building materials as heroic elements that were both visible and tangible may not always have been a formal preoccupation of modern architects, but the heroic quality of constructional elements remained for modern architects an unchallenged model for putting together, for building their abstract concepts. The belief that traditional or heroic materials constituted the basis of building construction, if not always the conceptual basis of the architecture, became increasingly untenable in the 20th century because the underlying basis of architectural technology underwent a radical transformation. The reasons for and the results of this transformation can be summarized as follows. Steel and reinforced concrete frameworks, together with newly invented elevators, made it possible to develop tall commercial and residential buildings. The obsolescence of load-bearing masonry walls in this context created both the possibility and the incentive for reducing the thickness and weight of cladding systems. Air conditioning as part of mechanical ventilation systems, and therefore the ability to eliminate natural ventilation, made it possible to think of the building envelope as a skin or an envelope rather than as wall and window, while the elimination of the requirement for natural ventilation also permitted deep floor plates and formal geometries that were no longer constrained by the need to create rooms with windows. The relatively high cost of mechanical air conditioning provided an incentive to develop and deploy thermal control layers, insulation, at the building perimeter. And problems with failed sealant joints, condensation, polluted outside air, increasing energy costs, and water intrusion led to the conceptualization and deployment of rigorous control layers for vapor, rainwater, and air, in addition to the thermal control layer mentioned earlier. Now, it is important to emphasize the fact that what had previously controlled rainwater, vapor, air, and heat loss, the thick and more or less monolithic masonry walls of traditional construction, were the same elements that largely defined the architectural expression of traditional buildings. That is, architecture grew out of and supported this underlying technology, just as the technology supported the architectural expression. However, while the technology of control layers has migrated from the heroic materials of traditional architecture to the separate, optimized, and non-heroic membranes and insulative materials characteristic of contemporary construction, formal architectural design in the 20th and early 21st centuries largely remained stuck in the paradigm of traditional and heroic material expression, not only ignoring this profound technological shift, but actually moving in directions that exacerbate problems of vapor, air, and rainwater intrusion, as well as energy efficiency. In the new paradigm for architectural technology, 4 control layers need to occur consistently at the boundary between inside and outside space in order to control these 4 environmental factors: rainwater, vapor, air, heat. Wherever a control layer's integrity is violated along that boundary, the potential for problems increases in the following ways. Thermal bridges, that is, discontinuities in the thermal control layer, not only may lead to unintended heat loss or heat gain, but may also alter the temperature gradient between the outside and inside surfaces of the enclosure system, leading potentially to condensation, whether on interior surfaces, exterior surfaces, or interstitially. Such condensation may lead to structural damage, non-structural damage, and to the growth of mold. As an example, pictured here, the Aqua Tower was characterized by Joseph Strebreck in the ASHRAE Journal as, quote, a thermodynamic obscenity that takes your breath away, an 82-story heat exchanger in the heart of Chicago, end quote. Holes or gaps in the rainwater control layer obviously increase the potential for water to enter the building in unintended ways. This is my architecture building at Cornell with the bucket catching rainwater from the roof. Water is probably the single most damaging element in buildings when not properly controlled. In its presence, wood may rot or decay, ferrous metals may rust, dissimilar metals in contact with each other may undergo galvanic corrosion, gypsum board may be damaged, mold or mildew may grow, and so on. Holes or gaps in the air control layer can increase the probability that air will move through the enclosure wall or within the enclosure wall in unintended ways. All sorts of negative consequences may result. In particular, energy may be lost in much greater quantities than from discontinuities in the thermal control layer, since pressure differentials between outside and inside areas can drive large amounts of unconditioned air into the building while driving large amounts of conditioned air out of the building. And such unintended patterns of air intrusion can also wreak havoc on HVAC systems and create unexpected condensation within enclosure walls as conditioned or unconditioned humid air finds its way onto cold surfaces outside or inside the thermal control layer. Where a vapor control layer is not properly configured, or where an unintended vapor control layer is created by the inappropriate use of low permeance materials, for example, using vinyl wall covering in air-conditioned spaces, water vapor can migrate through enclosure wall assemblies, whether originating on the outside or inside of buildings, and condense on cool surfaces. Assuming that the various control layers are properly configured with respect to each other, so that, for example, an air barrier is not positioned within the enclosure wall assembly in such a way that it prevents water or vapor from draining or drying out. In those cases, the primary task is to make these control layers continuous. This is not particularly easy to do because control layers are most efficiently deployed outside the building structural frame so that they are not constantly interrupted by interior partitions and floor ceiling assemblies, and so that the building structure is protected from thermal changes and other environmental damage. Because they're deployed outside the building structural frame, they must be supported by or connected to the building structure in some way. Unless they are adhered or glued to the building structure or to some sort of backup surface or substrate supported by the building structure, then their means of support, whether clip angles, bolts, screws, nails, etc., invariably penetrate not only the control layer being supported, but also any control layers positioned between the control layer being supported and the structural substrate. Another image from the architecture building at Cornell showing its construction and pointing out that even if all the control layers are light enough so that they may be adhered without the use of penetrating fasteners, the outer rain screen cladding material needed not only to establish some sort of architectural presence for the building, but also to protect relatively delicate control layers from various forms of damage, and in some cases to create an air cavity or pressure equalization chamber. This cladding still requires some sort of fastening system that invariably must penetrate the control layers it covers and protects. Roof systems require the same control layers, but have different problems to reconcile, in particular problems with penetrations for mechanical equipment or skylights, and transitions between vertical sloping or horizontal surfaces. In the image, you can see that stone panels, the cladding, they're supported by these large clip angles which penetrate the thermal control layer. In other words, creating thermal bridges right through the insulation, rather than being deployed outside the insulation layer and being fastened back to the structure using some other smaller steel or stainless steel or carbon fiber pieces. This illustrates a fundamental contradiction in the theory of control layers, but it is a contradiction that can largely be overcome both by minimizing these inevitable penetrations and by detailing them explicitly where they occur, for example, at windows or other openings, penetrations, and at the fasteners themselves, in order to maintain the continuity of the various control layers that would otherwise be interrupted. This strategy, however, is compromised when the architectural design itself, not just the inevitable encounters with windows, penetrations, and fasteners for cladding support, has a conceptual basis rooted in the expression of discontinuity. Such discontinuity takes many forms, and it is not my purpose to document them all, or to suggest that all contemporary architectural expression is aligned with this tendency. The important point is this: where conceptual or schematic design is understood as a process of abstraction in which formal ideas can be developed without any consideration of control layer continuity, where contemporary modes of representation can capture virtually any formal geometry, where structural and energy analysis software can provide numerical validation for the most complex and indeterminate geometric models imaginable, and where architecture culture in particular, or in general, and generative design methods in particular, encourage a disjunction between formal conceits and constructional logic. In those cases, the probability of encountering problems with control layer discontinuities dramatically increases. The logic of control layer design in modern construction cannot simply be ignored. Describing the Wexner Center for the Arts at Ohio State University, designed by Peter Eisenman in 1989, Robin Pogrebin wrote that, quote, "It would seem embarrassing for any architect, let alone one as prominent as Peter Eisenman. You design a museum, your first large-scale work, a breakout project whose exterior scaffolding design, a virtual celebration of impermanence, sets the architecture world a-buzzing. Within just a few years, however, cracks start to show. Quite literally, the skylight leaks, the glass curtain wall lets in too much light, threatening to damage delicate artwork. The interior temperature swings by as much as 40 degrees some days," end quote. Different control layer problems plague the Stata Center at MIT, designed by Frank Gehry in 2004. Quote, "MIT has settled its 2007 lawsuit against the architects and builders of the Ray and Maria Stata Center. MIT's lawsuit cited design and construction failures in the building. These included masonry cracking and poor drainage in the amphitheater, mold growth at various locations on the brick exterior vertical elevations, persistent leaks throughout the building, and sliding ice and snow," end quote. The problem is that in a world of architectural production driven by competition, any logical constraint on a designer's freedom of expression leads the designer, perversely but inevitably, to explore precisely those forbidden places outlawed by prevailing conventions. In defying such logic, the designer seeks to defamiliarize what has become so commonplace that it is no longer capable of eliciting an aesthetic response, and therefore serving as a useful mode of competition. This is the heroic conceit of the contemporary avant-garde, to confront quote unquote danger in whichever of its manifestations appears as an appropriate target at any given point of time. Joseph Campbell, the American theorist who wrote about shared world mythologies, in particular the journey of the archetypal hero, abstracts from the culture of competition that motivates artists to embark on such counterproductive heroes' journeys, seeing only the mythical and idealized shell of heroism in such attempts. He says, quote, "Artists are magical helpers. Evoking symbols and motifs that connect us to our deeper selves, they can help us along the heroic journey of our own lives. Over and over again, you are called to the realm of adventure. You are called to new horizons. Each time there is the same problem. Do I dare? And then if you do dare, the dangers are there, and the help also, and the fulfillment or the fiasco. There's always the possibility of a fiasco, but there's also the possibility of bliss," end quote. Ironically, an inattention to building science is precisely what this version of heroism entails. Architects are not so much, quote, "helping us along the heroic journey of our own lives," end quote, but rather creating out of thin air a heroic journey for themselves, leaving the world of safe, predictable constructions, proposing buildings that have both the appearance and the reality of danger, where danger comes from challenging notions of aesthetic and sometimes literal comfort, challenging class-based conventions regarding the economy of means, and especially challenging forces of nature such as gravity or rain or snow, and then returning in glory after having confronted the agents of conformity, whether owners, users, public officials, etc. And for such heroes, having proposed or built such a brave thing with all the attendant risks of failure is a badge of honor. Peter Eisenman, in his interview with Robert Pogrebin, boasts that, quote, "There's not an architect I know that doesn't have problems with important buildings," end quote. Abstraction in and of itself is not directly the cause of non-structural building failure. Rather, problems emerge due to the interaction of several factors that relate to the use of abstraction in modern architecture, not all of which are necessarily present in any given instance. So here are 9 of such factors. 1, abstract ideas tend to proceed rather than evolve from considerations of a technical or functional nature. This is partly a result of a misplaced confidence in the power of science to compensate for any a priori design decisions, and partly a result of an education in construction derived from empirically based rules that provide neither the theory to grasp nor even the vocabulary to define the issues that have become relevant in the design of enclosure systems. As a result, abstract, quote, volumes brought together in light, end quote, Le Corbusier's idealized definition of architecture, first published in 1920, often experience problems, and they also are invariably brought together in rain, wind, and snow, and subject to unanticipated environmental pressures. 2, whereas a steel or concrete structural framework or an environmental control system can be conceptually and physically separated from the rest of the building, permitting a specialized process of engineering design that supports the architectural concept, it is difficult to see how the enclosure of a building can be dealt with in an analogous manner without reducing the architect's role to a purely schematic one. From the standpoint of both traditional and modern architecture, the enclosure to a great extent is the architecture. Delegating the detailed design of enclosure to others, aside from loss of prestige and remuneration, opens up the risk of compromising the abstract basis of the design. Vertical surfaces may terminate in unwanted copings. What was conceived as abstract void may appear as conventional window, and the precise articulation of formal elements based on subtleties of alignment and proportion may suffer. 3, the architect, while maintaining control over the building's external surfaces, tends to resist serious applications of engineering criteria to the design of building envelopes. Within the academic design studio, as well as in practice, such criteria are perceived as threats to the freedom of formal invention that are characteristic of modernist abstraction. In the words of the Dutch painter and theoretician Piet Mondrian, quote, "If one takes technique, utilitarian requirements, etc., as the point of departure, there is a risk of losing every chance of success. For intuition is then troubled by intelligence." I love that quote. 4, the risk of enclosure failure is neither as obvious, immediate, nor usually as catastrophic as is the case with structural failure, for example. So there is less pressure to develop the necessary theoretical or empirical basis. Details often seem reasonable when initially conceived and executed, as their intrinsic defects may be far from obvious. In fact, obvious or common sense solutions are sometimes problematic. For example, the popularity of non-redundant barrier walls may result from a common sense approach to the problem of rain exclusion. When it is raining, we wear a raincoat or Macintosh, so why not treat our buildings likewise? Additionally, many non-structural failures take years to manifest themselves. Even short-term or accelerated tests may give misleading indications. A tentative judgment only may be possible, based on technical knowledge and subject to confirmation in due course by observation. Cracking and bowing of marble cladding panels on the Standard Oil Company headquarters in Chicago, the name was subsequently changed to the Amoco building, and it's now the Aon Center. These were noticed first almost 7 years after initial construction. They became increasingly prevalent only within 13 years of construction. And they finally led to the complete replacement of the facade after 19 years. Such non-structural failures are often costly, inconvenient, and dangerous, but they are rarely catastrophic. Number 5, because the traditional means of dealing with enclosure is primarily based on empirical rather than on scientific knowledge, most modern architects do not necessarily know what they don't know about the subject, and are thus more inclined to either extrapolate inappropriately from prior experience or simply invent constructional details based on a superficial understanding, that is, a misunderstanding of the complex forces at work. In other words, the empirical basis, the experimental basis for much prior constructional success having little basis in a theory of building science, is discarded without the modern architect knowing exactly or even approximately what is being lost. For example, if a 24-inch thick load-bearing masonry wall seems to work well at keeping water out, it may not be clear why 8-inch thick cladding supported on a structural frame wouldn't keep water out just as well. The process of abstraction, unmediated by any serious building science, reduces the complex behavior of specific wall types to formal ideas. The wall becomes a, quote, plane or a surface or a constituent part of a volume or mass. Even the origin and purpose of the pitched roof, understood traditionally as a culturally specific response to environmental conditions, rain and snow, is dismissed by R.S. York, architect and author of The Modern House, as a structural anachronism made obsolete by the employment of frame construction and concrete slabs. 6. There is also a tendency to overestimate the durability of many modern systems and materials, as modern becomes identified in popular culture with overcoming traditional labor-intensive practices. Habits of maintenance, characteristic of traditional building practice, continual repair, replacement, pointing, painting, etc. All these things are loosened from their traditional bearings. While expectations of permanence, toughness, and resiliency become part of the culture, if not the reality of modern materials, two other factors make decisions regarding durability more difficult for the architect. First, it is not easy to obtain definitive information on the performance characteristics of complex components, equipments, and systems. Knowledge is limited because those who have it tend to view it in a proprietary manner and are often reluctant to share it. Competing manufacturers vying for market share may not always be inclined to objectively compare their products with others. And second, the desire to extract the maximum profit from investments in commercial buildings tends to encourage both marginal construction practices and deferred maintenance. 7, a disdain for conventional applications of technology may seem somewhat paradoxical in light of modernism's invocation of precisely this technology in its manifestos opposing traditional modes of building. But several factors are at play. There is first a distrust of and backlash against technical solutions within so-called postmodern culture. And this phenomenon lends support to architectural forms that express these feelings by literally distorting that which appears as logical within modernist practice. Second, with the victory of modernism over traditional construction practices, what was heroic and radical in the deployment of steel and reinforced concrete frames becomes conventional. Given the cyclic movement of fashion, it is inevitable that an avant-garde style, once integrated and accepted within popular culture, must give way to something new. The negation of the logic embedded within modernist conventions becomes the stylistic path of least resistance. And third, technology is still expressed, even fetishized, in its irrational manifestations. Glass is reimagined, no longer merely as the void in modernist abstraction, but as the visible and universal boundary between inside and outside. Cladding is similarly abstracted as universal surface. Structure is bent, angled, cantilevered, hyper-articulated, and so on, using techniques based on distortion or other forms of defamiliarization. 8. Modern attitudes to construction tend to focus on structure and cladding as quote unquote heroic materials through which the ideas of the designer are made visible. In the postmodern reaction to modernism, such attitudes survive largely intact. Critiques of modernist idealism still rely on structure and cladding as expressive formal elements. Yet as building science evolves, the failure to acknowledge an emerging paradigm shift in the actual requirements of building, that is, from the use of relatively unsophisticated enclosure strategies characteristic of modernism, to the more subtle application of non-heroic systems based on control layers to control air, vapor, water, and heat flow, and incorporating issues of sustainability. This is increasingly problematic. And number 9, magic pill. At the same time, Even as the expression of technology, as a manifestation of rationality, is subjected to formal critique, technology itself is not actually rejected, but in fact assumes an almost mystical aura. If the engineer of modernism, as Le Corbusier wrote in 1923, quote, inspired by the law of economy and governed by mathematical calculation, puts us in accord with universal law and achieves harmony, end quote, the postmodern engineer rejects the constraints of economy, values ambiguity over harmony, and relies on complex numerical methods programmed within the black box of sophisticated analytical software to transcend the limitations of traditional mathematical calculation. Cecil Balmond, one of the more notable contemporary engineers, writes, quote, structure need not be comprehensible and explicit. There is no creed or absolute. It can be subtle and more revealing. It is the richer experience if a puzzle is set or a layer of ambiguity lies over the reading of structure, end quote. Technology in this context is thought to possess almost limitless power to overcome projects originating in any predetermined form, no matter how arbitrary and illogical. Form, in other words, can be abstracted from virtually all considerations of a technical nature. And technology, much like the digital improvements common in photography, music, and film, can compensate for what might have been a hopelessly misconceived or inadequate performance. The singer-songwriter producer Ben Folds captures this sentiment perfectly in his 2001 song, I'm rocking the suburbs, I take the checks and face the facts that some producer with computers fixes all my shitty tracks. The problem with this attitude, at least in architecture, is twofold. First, such technical quote unquote solutions focusing only on internal criteria of success may lose sight of other criteria external to the immediate problem. For example, a solution to the problem of environmental control may end up requiring excessive energy use. And second, such an attitude is just unrealistic. Unlike structural frameworks or other relatively straightforward technical systems within buildings, the reliability of the building envelope is threatened by thousands of highly complex and often unpredictable interactions among building materials and systems, subject to differential movement, chemical reactions, environmental agents, construction and maintenance operations, and so on. Architectural form based upon empirically validated principles of building science, form that minimizes the collisions amongst these countless variables, has a greater probability of success than does architectural form that either willfully distorts these principles or operates as if such principles can be applied after the fact. In closing, I don't want to leave you with the impression that artistic expression can or should be abolished in works of architecture. Hannes Meyer, in the final two paragraphs of my book, I talk about him, the Swiss architect who directed the Bauhaus from 1928 to 1930, and who famously attempted to devalue the role of the artist while emphasizing functional and technological issues within the curriculum of the Bauhaus. Such an extreme formulation of the art-science duality is only marginally relevant to the argument advanced here, since there is no reason to abolish or even to denigrate the role of artistic expression within the design process. Even if, as Meyer wrote in 1928, quote, the idea of the composition of a dock is enough to make a cat laugh, end quote. Such a finding should not be extrapolated into the realm of human cognition. To an extent unique among all creatures, humans construct and in doing so compose our world, irrespective of any desire, however rational, to prioritize function and technology. The American neuroanthropologist Terence Deacon argues that not only is the compulsion to treat objects or actions as signs a characteristic of the human aesthetic faculty, but most importantly, we almost can't help ourselves. The question, therefore, is not whether art should be eliminated from architecture. Art is unavoidable. The more important question considered herein is whether and how the art of architecture can adjust its trajectory so that it aligns with the more fundamental requirements of building science. Thank you. Let me unshare. And maybe there's a few minutes for questions if anyone has any.
I have a question.
Let me make my volume a little louder so I can hear you better. Hold on a second. Go ahead.
Where is your book available?
Well, if you find it on Amazon, it's probably the easiest way. I have you can go to my website, johnochshorn.com, and you'll find links to all of that stuff. But you can Google Building Bad in Amazon and you should come up with it.
Okay, thank you.
Thanks for the question.
Yeah, I would just like to add, this was a great presentation, and I wanted to thank you very much for doing this for us. And it also is in line with us trying to provide unique, interesting programs that are a little bit different than the regular lunch and learns you get. So thank you very much, John, for doing this.
I appreciate the opportunity. So long to everyone.
Okay, bye.
Thank you.